Hi, I'm Professor Svernigblegedeh. Here at the university, I hold a joint position in the mathematics and music departments. A long time ago, I applied for this job. As part of the interview process, I was asked to give a lecture to a calculus class, and then to perform a piece of music. I'd like now to share with you the lecture I gave that day, and then the song. I remember it very well. It was the day right before Thanksgiving break. The class had just recently learned about the great ancient mathematician Archimedes, who essentially used calculus, using what we would today call limits and Riemann sums, to calculate areas of regions. For example, in this way, one can derive the well-known formula for the area of a circle, pi r squared. So, for my lecture then, I decided to use limits to derive the well-known formula for the circumference of a circle, 2 pi r. Then by slightly changing the point of view, I derived a surprising and not so well-known fact about the number pi. When you see it, I think you'll be just as shocked as the class was that day.
To begin, take a semicircle of radius 1. We'll find the circumference of this semicircle, which we call S for semicircle. The circumference of the full circle is 2 pi, so our goal is to show that S is half of that, namely pi. The plan is to approximate S with smaller and smaller line segments. Then take a limit. We begin with the diameter of the circle, which we call L1. Think L for line. Clearly L1 equals 2. Next, in purple, we draw 2 chords on the circle, in this way getting closer to S. The union of these 2 chords we call L2. Using some geometry, you can work out that L2 equals 2 times the square root of 2. We continue in this way, drawing more and more chords, more of these purple chords, and making them smaller and smaller so that they get arbitrarily close to S. After n steps, we'll have n small chords. Let L sub n be the union of those n small chords, as shown here. As you can see, the limit as n goes to infinity of L sub n is S. Well, that's because in the limit, the set line segments approach the semicircle. Well, 180 degrees is pi radians, so the angle for the semicircle is pi radians. Dividing that equally into n pieces, we see that each chord is the base of an isosceles triangle, where the angle opposite the purple chord is pi over n. The other sides of the triangle are each 1. Using some trigonometry then, we can work out the length of the purple chord. Let's rotate the triangle so that the purple is at the bottom. Dropping a perpendicular cuts the angle in half for an angle of pi over 2n. Half of the purple chord then equals sine of pi over 2n. So the full purple chord is 2 times sine of pi over 2n. Back to our picture, we have n purple chords, each of which, we now know, is 2 times sine of pi over 2n. So when we add up all the purple, we get that L sub n is n times 2 sine of pi over 2n, which we can simplify a bit. Now that we know L sub n, we can work out the limit as n goes to infinity of L sub n in order to find S. S will be the limit as n goes to infinity of 2n times sine of pi over 2n. For reasons that will become clear soon, let's write 2n as pi times 2n over pi. Multiplying by 2n over pi is the same as dividing by its reciprocal. Notice that pi over 2n now appears in both the numerator and the denominator. So let's set that equal to x. As n goes to infinity, pi over 2n goes to 0. So we replace the limit as n goes to infinity with the limit as x goes to 0. And now we see the reasons for these algebraic manipulations. Ignoring the pi, it's just a constant after all, what remains is the limit as x goes to 0 of sine x over x. But this is a well-known limit. When you first encounter it, it's not obvious at all what that limit should be. Sine x over x is not some bland, boring limit. It's quite a spicy limit. And as you may know, the limit as x goes to 0 of sine x over x is 1. So our limit here then works out to pi times 1. In other words, pi. Well, that's the good old Archimedean value of pi. That is 3.1415, etc. By the way, if you play this same game using radius r instead of radius 1, you'll get pi times r. And so if you take the full circle instead of just half the circle, you'll get the formula for circumference, 2 pi r.
In honor of the occasion, at this point in my lecture, I took off my button-down shirt and revealed a pi-themed t-shirt.
Well, now let's change our point of view. Instead of approximating the semicircle with straight line segments, let's instead approximate a line segment with semicircles, and we'll just see what happens. We start with the line segment L. This is the diameter of the circle we've been considering. So as you can see, L equals 2. For our first approximation to L, we take the entire semicircle, which we call S1. Well, as we worked out previously, S1 equals pi. S2 will be the union of two semicircles, as shown. It makes something of a yin-yang kind of shape. For each of these two semicircles, the radius is half of what it was before. That is, the radius is 1/2. Since the length of the semicircle is pi times the radius, the length of each semicircle is pi times 1/2. That is, pi over 2. So the total length of S2 is 2 times pi over 2, which equals pi. And now we play the same game all over again. S3 is the union of 4 semicircles, as shown. The radius is now half of what it was at the previous step. That is, the radius is 1/4. So the length of each semicircle is pi over 4. There are twice as many semicircles this time. Now there are 4 semicircles. So S3 is 4 times pi over 4, which equals pi. Well, in the next iteration, which is not shown here, you would get twice as many semicircles, each of which would be half as long. Like for S4, you would get 8 times pi over 8, which equals pi. For S5, you get 16 times pi over 16, which equals pi. Every time, you get pi. So in other words, Sn equals pi for all n. That means when we take the limit as n goes to infinity of Sn, we are really taking the limit of the constant sequence, pi. So the limit is pi. On the other hand, the limit of the Sn was L. So the limit is 2. Therefore, we conclude that pi equals 2. Many people prefer to write out more digits of pi, so if you like, you could say that 2.0 is the value of pi. And so it's farewell to Archimedean pi, the good old 3.1415. This is quite surprising, to say the least. As you can imagine, the calculus class I taught that day, right before Thanksgiving, was rather shocked to learn that the value of pi is 2.0.
That concluded the math portion of the lecture, and then it was time for the music. I took out my guitar, handed some sheet music to the class's regular professor, a trained vocalist, who was kind enough to accompany me on the song. You know, just picking up this guitar, it brings me back to that day before Thanksgiving, all those years ago. I can almost see it in my mind. Me playing guitar, the calculus professor singing, the class reacting. It went something like this. A long, long time ago, Archimedes calculated volume Riemann sums.
And I knew if I drew straight lines, that at some point that I would find the circumference within epsilon it comes. I drew some small chords on the circle, and when we add up all the purple, the limits work out nicely. They come out super spicy. But when we change our point of view, we get a fact that's known to few. This result is truly new. We prove that pi is true. What happened to good old 3.1415? The semicircles in the limit form a straight line, so 2.0's the value of pi. 2.0's the value of pi. Oh, you know, I'm actually wearing a pi shirt.
I'm wearing a pie shirt as well.
So now it's confession time. There is no joint position. He's no friend of mine. There's no job on the line, and 2 is not the value of pi. Sing it, 2 is not the value of pi. This proof contains a bit of a lie. See if you can figure out why. In the meantime, eat some turkey and pie.